Okay, let me give you like 5 minutes to copy this example down. This example is, the book has many good examples. This example we're doing is actually a homework problem, or one like one of your homework problems. And so I'm doing it because I want to, try to give you a variety. Let's take a few moments to copy the example down, and then we'll discuss the solution. Okay, there's a lot of good things in this problem. Okay. Okay, a few more moments here to copy the example down, and then we'll start on it. Okay. It's hard to believe that your third exam is next week, next Thursday.
We have 4 regular exams plus the final, correct?
That's right, Christopher. 4 regular exams plus the final. That's correct.
Okay.
Some professors for 3-credit courses only give 3 exams and a final for testing, but I like to give 4 just because, well, it breaks the material up a little more, and it gives students a chance to bring grades up if they don't do as well on one exam as another. All right, well, let's take a look at this problem here. In this problem, we have a force of 2 pounds, and it stretches the spring 1 foot. So based on that information, we'll be able to get the spring constant K of the spring. And then let's see, a mass weighing 2 pounds is attached to the spring, and the system is then immersed in a medium that offers a damping force that is numerically equal to 0.4 times the instantaneous velocity. Suppose also that the mass is initially released from rest from a point 1 foot above equilibrium position. Okay, so we want to find the first time at which the mass passes through the equilibrium position heading upward. Okay, so again, we have a mass attached to a spring, and we need to model the motion of that mass. We need to model the motion. So we need to, so how do we start this problem? What's the first thing we need to do to, I mean, there's a lot we need to do to get to the point where we can answer the question. And Matthew's right. We have to set up that differential equation. So that being said, let's see, Thomas, what's FBD mean? FBD. Thomas chatted something in the window, a free body diagram. Well, yeah, I mean, I know in my mind what we have. We have we know in our minds we have a mass attached to a spring. It's a vertical spring. Depending on the damping force, it's going to determine how this mass behaves, its motion. We have, it's not going to be an undamped system because we have dampening present, but it could be underdamped or overdamped. We have to really put everything together in the differential equation to determine this. And so let's go ahead forward and do that. So what we do, the differential equation we use is, this is the general differential equation from section 5.1. So you have mass times the second derivative of position x. So that's mass times acceleration is equal to negative kx minus beta times the velocity, dx dt, plus an external driving force. K is your spring constant, and beta is your dampening coefficient. So for this spring, well, let's figure out what these values are. There's no external driving force, so F of t is 0. Okay. Beta is 0.4. Okay, that was given to us. And then the mass in this case is going to be 0.1 slugs. And so to get that, I take, let me see here, one moment. To get that, we have to take the fact that the mass weighs 3.2 pounds, okay, and we divide that by acceleration due to gravity, which is 32 feet per second squared. All right, how many have certainly learned that figure before, 32 feet per second squared?
Hey, Professor, can you explain why we do that?
Sure. Oh, why do I divide?
Yeah, why do we divide the pound?
Well, actually, I can explain. I actually have an explanation right here. I understand where you're coming from. So you agree that force equals mass times acceleration, right?
Right.
And weight, when weight is in pounds, pounds is a unit of force. So weight is in pounds. Well, yeah, a pound is a force, right? Pound is a force. That's what I mean. So force equals mass times acceleration. But in this case, the weight is going to equal mass times acceleration due to gravity. But then, okay, how would we find the mass then here? Well, we would divide both sides by gravity, and so mass is equal to weight divided by gravity. And that's how I come up with the mass here.
So if we were given kilograms, we wouldn't divide by 9.8?
That's correct. Kilograms is mass. You would not need you would not.
Okay, that makes sense. That was Yeah.
Yeah, because if
Sure.
you're using the metric system, you use newtons because Newton, yeah, you use newtons.
That's correct. That's correct. That's right. Well, and so now, okay, we got to figure out that spring constant K, and we were told that a force of 2 pounds stretches the spring 1 foot. Okay, so that means K is going to have to equal 2. And so given that now, we can substitute all of these values in the differential equation, and we come up with this differential equation here. Okay, and I'm using the prime notation for the differential equation. I don't have to, but it's a little easier to write it. Are there any questions up to this stage right here? All right, well, certainly. Right, okay, okay. So, of course, we want to solve this second order differential equation using techniques we learned in sections 4.3 and 4.4. And so I have to write the linear differential equation in the standard form. And well, of course, I get a 0 on the right-hand side. But then, to make my life a little easier, I'm going to divide for this part right here. Let me just clear this here. For this, for the differential equation here, I'm going to divide through by 1/10, and that's going to get me this differential equation where I have a coefficient of 1 in front of x double prime. So, okay, I have a second order differential equation with constant coefficients, and what do I need to find? I mean, what do I need to do to solve that differential equation? What's the technique? We have to find what kind of equation. I'll give you a hint. It begins with an A. There we go, Antonio. Good. An auxiliary equation. Okay, and so that's what we're going to do next. Are there any questions before we move to the next page? All right. All right. Well then, all right. Now this is a second order. Well, all right. So the auxiliary equation is a second order. So we don't need to use MATLAB to help us solve it. I mean, we could, but hey, we know how to use some quadratic formula here. And so we do that, and it turns out that our roots to the auxiliary equation are going to be complex numbers. M will equal -2 plus or minus 4i. And so this means then that, well, this is what the general solution is going to be right here. Let me give you a moment to catch up. Let me know if you have any questions.
Dr. Dudy, it seems like there's a -1 on the right of that. That's not included in that, right? I don't know if that's like.
Let's see here, a -1.
Yeah, it's to the right of
Oh
the
yeah,
check mark.
this here. Whoops, hold on. This here is nothing.
Okay.
That's nothing there. So let me ask you: would this? So now the spring will the mass behaves, the position of the mass about the equilibrium, you know, it goes above equilibrium, below equilibrium, above, below, is the position of the mass. Well, is the mass eventually going to come to rest, or will it come to rest eventually based on this position function? Good. That's right, Andrea. That's right, Zachary. It will, because the e to the negative t, as t goes to infinity, e to the negative t is going to dampen the position. So even though it's oscillating, it oscillates. The amplitude gets less and less and less with time. That's right, and eventually it'll settle down. That's right, Michael, to equilibrium. Would this mass spring system be considered? We know it's not undamped. But would you consider, would it be called underdamped or overdamped based on that solution x of t? Okay, and I'm getting I'm just curious. My initial instincts were to say underdamped. Michael is in agreement with me, but let me tell you why. The mass is it does approach equilibrium, but in an oscillatory fashion. Okay, it isn't like it just like if you look on in section 5.1, figure 5.1.10. That's figure 5.1.10 in your ebook. You'll see that the underdamped system, that this equation would go with an underdamped system. Okay, so good, you know, good participation there. Now also we have a few more pieces of information that we have here. Let's see, wait, Matthew says, one moment here. Overdamped is when it comes to, so Matthew's saying overdamped is when the mass comes to rest, not through equilibrium, where underdamped comes to rest through equilibrium. Let's see, I got to be a little careful on that. That would seem, I would agree with that. I got to be a little bit careful on this because, but that seems, at least initially, to be correct. I mean, overdamped means the mass comes to equilibrium very quickly. It is not oscillating. It is not oscillating about equilibrium. It comes very quickly to rest. So that intuitively, Matthew, what you said in the chat window makes sense to me. Okay. So now we want to solve for our coefficients C1 and C2, and we can do that because we have initial values. We're told that the mass is at time 0. The mass is at rest from 1 foot above equilibrium position. Well, 1 foot above means at time 0, x of 0 equals -1. -1. So remember how the vertical axis works. It's sort of the opposite of what you expect. When the mass is above equilibrium position is when x equals 0. So when the mass is above equilibrium position, the x values are negative. When the mass is below equilibrium position, the x values are positive. Okay, and you can refer to figure 5.1.2 in section 5.1 to see that that orientation. And also we're the mass is released from rest, so that means that x prime of 0 equals 0. Okay, the mass is just released from rest. So we're going to solve for C1 and C2 by, well, we have to take the derivative of x. Okay, so let me give you a moment to look at that. One moment. Hey, Cliff, how you doing? Hold on, buddy. I'm actually doing remote teaching, but let me get Kurt. One moment. Hey, Kurt. It's Cliff. It's Cliff. Yep. All right, nobody, he's coming to the phone, but. All right, buddy. It's Cliff. You're welcome. Okay, sorry for that interruption, class, but all right, so okay, so of course I use the product rule, the chain rule here to get the derivative of my position function. And you know, I worked it out, but of course you can always confirm things, derivatives using MATLAB. I know sometimes the derivatives are a little messy, so it's nice to have MATLAB help confirm you know, your derivatives when you take them. You don't want to forget how to differentiate, and you do know that on exams I like to see work, but you know, here we go. Are there any questions before we move to the next page?
Yeah, so for these four T's, some of them are in parentheses here, like sort of some of the like
Yeah, you're right. I guess I was a little inconsistent there.
I just want to make sure like all the sines and cosines only have 4T in the parentheses.
They do.
Okay.
Here, I'll put the parentheses here as well. And I don't always put parentheses around my angle. I just did here because it kind of helped me remember to do the chain rule, essentially. All right, good question, Matthew. Are there any other questions? All right. Well, all right. And so, of course, now we are going to substitute t equals 0 into our x of t position function and our derivative of t, our derivative of position. So that being said, then we'll go to the next page, and here's where I do the substitution. Okay, and when I substitute t equals 0 in my position function, I determine that c1 equals -1. And I'll use that then here. And I substitute t equals 0 in the velocity, right? The derivative of position is velocity. So my velocity function, I substitute t equals 0 in and do the work just like you would do the work, right? Okay, and based on that, I get C2 equals -0.5. Now let me give you a moment to catch up here and let me know if you have any questions. Okay, whoops, hold on. Okay, so now we have then the, concrete position of our mass. We have what we solved for C1 and C2, and now we have this function for the position of the mass. And notice, class, also that the C1 goes with the cosine term, C1 equals -1, and the C2, which equals -1/2, goes with the sine term. So in order for things to work out correct in like WebAssign and getting answers, you have to have your C1 value go with the cosine function, and the C2 value be that goes with the sine function. Okay, in that order. Now, okay, so we have the equation that for the position of our mass. Now we want to see, when is the first time at which the mass is going to pass equilibrium position headed upward? Well, in order to answer that question, I have to get this position function in a different form. That's going to involve an amplitude and a phase shift. So let me show you. We already actually did that on a previous problem, but I'll show it here for this problem. May I move to the next page? Are there any questions?
I'm good.
Okay. All right, very good. Then here we go. So based on my position function here, I plot the coordinate C2, C1. Okay, and this is justified in the textbook why this approach works. But I plot the coordinates C2, C1, which is -1/2, -1. That's in the third quadrant. And so my phase shift angle phi, this phase shift angle phi, that angle is going to be in the third quadrant. And I have to figure out what that angle is. Okay. Well, all right. And remember, you ought to be able to double click on your screen and to blow the picture up a little bit. As always in trigonometry, it all boils down to the reference angle. So in the diagram for this right triangle here, hold on, let me get it like that. Right, we have a right triangle here. The reference angle is angle alpha. And so the tangent of alpha is, tangent is opposite over adjacent. So the opposite leg is -1. The adjacent leg is -1/2. Or you can think of it as y over x. That's fine. That equals 2. And on your calculator, if you do the arctangent of 2, you're going to get 1.107. Okay, but 1.107, that angle is not the angle phi. The calculator is going to give you angles that are either in the first or fourth quadrant by default. Okay, so if you think about it, this angle here, 90-degree angle, is pi over 2, right? Well, pi over 2, pi is 3.14. 3.14 divided by 2 is 1.57. So So in terms of radians, 90 degrees is approximately 1.57. So an angle of 1.107 is, in radians, is going to be in the first quadrant. So in order to find phi, you have to, I mean, I guess, let me maybe I can phrase it another way here. Let me maybe add a little something to the picture here. I have an idea. Okay, so okay, let me do this. Okay, this reference angle is also alpha, and alpha is 1.107. But phi is another 180 degrees past alpha. So that's pi. So you take the alpha and the pi to get 4.205, and that's your phase shift angle. Okay, does that help you see it a little bit? Was that helpful? Okay, great. Glad to hear that.
So I
Thank
guess
you.
that's just that simplified equation is just to make your calculations with it later simpler, right? Like, just is there any other reason you would get this simplified equation with just sine rather than sine and cosine?
Let me see, Matthew. Is there another reason? Let me see. Oh yeah, thank you, Andre and Thomas. Matthew, you're wondering about like this part here where I add the pi?
No, I'm saying like overall, this final step where you transform your equation, your x of t equation
Oh,
from the,
right, at the bottom.
yeah.
So, okay, all right. So, of course, the amplitude is going to be square root of 5 over 2, and then we get it in this form. Yes, the reason I get it in this form, now I won't always have to. Like, for instance, in some of your homework problems, the position function that we had previously, which was a linear combination of sine of 4t and cosine of 4t. Well, I got to be careful. It's a linear combination of e negative 2t sine of 4t and e negative 2t sine of 4t. That would be fine. WebAssign would take that. But to do this problem, I need to get my position function x in this form here. And you'll see why. You'll see why. But you won't always have to do that. Very good question.
So is that
So we want to find the first time at which the mass passes through equilibrium position headed upward. And let's see why this helps us, the position function in this form. May I go to the next page?
I have a question. Just
Oh, sure. All
how
right,
you
Antonio.
get this. So, is the way, like, I just don't understand how you get that bottom equation. Like, I see like the 4.25 and the amplitude in there, but I don't understand how you go from like what we had at the top to there. You know what I mean?
I'll tell you what. I think we'll have time in class for me to justify it.
Okay.
Why don't after I'm done with this example, why don't I go to the ebook and take you step by step through that? How does that sound?
Sounds good.
All right, we'll do that. We'll do that because it's worth doing. It's very much worth doing. All right, are there any other good questions? Okay, so, all right. Now, we want to find the first time at which the mass passes through the equilibrium position heading upward. All right, so, well, all right. So from what we have just done, it was shown that x of t is equal to the square root of 5 over 2 times e to the negative 2t times the sine of 4t plus 4.25. That's our equation of motion. And the mass is going to be in equilibrium position at times of t when x of t equals 0, or equivalently when the sine of 4t plus 4, the sine of the angle 4t plus 4.25, when that sine equals 0. Now, why is that? Well, here's your equation of motion. Will the e to the negative 2t part, will that factor ever equal 0?
No.
It will not. And so it's all depends on the sine function being equal to 0. If the sine function equals 0, the mass is in equilibrium position. So, okay, well, when is a sine function equal to 0? Sine function equals 0 when the angle is equal to multiples of pi. Right? If you think about the sine wave, anytime, like the sine of, what's the sine of 0? The sine of 0 is 0. What's the sine of 180 degrees? That's 0. What's the sine of 360 degrees? 0. So any multiple of pi, if the angle equals any multiple of pi, that's right, Zachary. Then then we're interested in that. So and so essentially now we're going to be able to solve then for t. We're going to be able to solve for t. All right, but we have to be a little bit careful because the mass because the well let me just the mass oscillates about the equilibrium with an amplitude that's getting less and less and less. But we're trying to find a very specific time at which the mass goes through equilibrium headed upward. So, that's one specific time. So, all right, well, let's say I'm going to try I'm going to try to solve for time when the angle is equal to 0. Well, if 4t plus 4.25 equals 0, t is going to be negative. But that's impossible because the initial time of the mass spring system is t equals 0, right? And so as time passes, the first time that the mass passes through equilibrium position headed upward has to be a positive time, right? That time has to be positive. So we can't allow for time t to be negative. Can't allow for that. So, okay, well, let's try the next, in other words, we'll cross that off our list. Next is pi. All right, well, when 4t plus 4.25 equals pi, t is going to be negative as well, which is impossible because we're initially starting at t equals 0 seconds. So that, got to take that one out. So you keep going until you find the right time. Next, we're going to do 2 pi for the angle. But let me give you a moment here. I'm sure you're probably copying a little bit. Please ask me any questions. Let me give you a moment here to catch up. Are there any questions at all?
Professor,
Yes, Michael.
since we have a sine 4t plus 4.25, the period of that let's say waveform is going to be 2 pi divided by 4,
That's
right?
correct. That's correct.
Why are we considering multiples of pi rather than multiples of pi all over 2?
Well, it has to do with this fact right here, that x of t will equal 0 when the sine of the angle 4t plus 4.25 equals 0. So all I care about is, I mean, it's like, okay, when is the sine of some angle theta equal to 0? For what values of theta? Okay, well, theta equals 0, theta equals pi, theta equals 2 pi, and so forth. Well, I'm treating this then 4t plus 4.25 is like theta.
Mhm.
Does that help?
It's just that I got into a problem when I was solving one of the homework problems, and I had to consider the period. It wasn't actually equal to 0. It was equal to some other value like that. And I had to the first solution I did was to equate to add 2 pi, to add multiples of 2 pi,
Right.
but it didn't go. I had to consider the period, so that's why.
Well, I'll tell you what. Is this Michael asking this?
Yes, it's Michael.
Okay. We can take a look at that after class. It's probably, I mean, the problems differ a little bit, and sometimes you have to do different things. But I know this problem. We're doing it right.
Okay.
But we'll take a look at that if you want a little bit after class. Not a problem.
Okay.
All right, no problem. Well, now we're gonna try 2 pi. We're gonna try 2 pi. All right. So in other words, we're gonna keep putting in multiples of pi until we get a positive time. We got to at least get a positive time before we can start talking about other things. And so, okay, I go to the next page. I use 2 pi next. And oh my goodness, here we go. T is going to equal 2 pi minus 4.25 over 4. Well, pi is 3.14, so that is going to give us our positive time. But does that mean that that's the answer? Not necessarily, because let's think about what we were told. We were told that the mass was released from rest 1 foot above equilibrium position. 1 foot above equilibrium position. So what's going to happen? The mass is attached to a spring, okay, and you release the mass, from rest. The mass is 1 foot above equilibrium position. What's the mass going to do? Is it going to go up or is it going to go down?
It's going to go down through the.
It's going to go down. So the mass has to go downward through equilibrium position first, and then it's going to go upward through equilibrium position next. It oscillates, but the first time it passes through equilibrium position, it's going to be doing it going downward. Well, we want to know the first time the mass passes equilibrium position headed upward. So this means that this time here, 2 pi minus 4.25 over 4 is not the right time. It's not the right time. That would be the time that the mass passes through, the first time the mass passes through equilibrium going downward. So to get the next time, the mass will go down. It passes through equilibrium going downward. It reaches, a certain point, and then it springs back up. Okay, so what are we going to have to do then to the 4t plus 4.25 to find that time? What are we going to have to set it equal to?
To the next multiple of pi.
That's right. And the next multiple of pi, that's right, Michael, is 3 pi. So that's the time that would work. And you could graph, this position function x of t, you could graph it on your TI, 84 calculator or use Desmos, and you could see that you could verify this time, graphically. You could verify it. But the thing is, the graph, it gets pretty tight, because of that e to the negative 2t power, the dampening on that, you have to usually adjust your window, because the oscillation gets smaller and smaller and smaller. So, but this one should be okay in terms of. And this is why we need to get the position function in that special form so that we can answer important questions like this. Has anybody maybe in a physics class had to, find a time when the mass is like a question like this? Has anybody seen this in their physics class? Similar type thing. Okay, thank you, Andrea. Andrea has.
Yeah, we needed to put it in the cosine form rather.
Right. Well, the code.
Amplitude
I mean,
cosine.
it shouldn't matter what form
Yes.
it's in. In terms of, I mean, the time should be, but of course, got to be careful here. The cosine function, the C1 and C2 might be switched. To be honest, I don't. I just really, this is the form I'm familiar with, but you just have to be
Yes,
careful.
Professor,
But
that's
I know
right.
WebAssign
Switch.
is once the sine wave, but what I'm saying is, and what Michael's saying is, in his physics class, instead of a sine of omega t plus phi, they use a cosine of omega t plus phi, and that's okay. You ought to be able to get the correct time. It shouldn't matter, but I would like you to try to use the form that we have here, for our book, just because it's well, it's like WebAssign. I don't want WebAssign to count your answer wrong or anything like that. You know what I mean? Okay. Are there any other good questions about this? Okay. All right. Let me bring up the ebook. Just give me one moment, class. Okay, so what I'm doing is in the ebook, I'm trying to I'm looking for the portion in section 5.1 where they justify this process where you get that phase shift and how you can, well, I mean, how you can write the position function in this form. I'm trying to find where they justify that. So give me just one moment here. I just got to find it. It's after example 1. If you have your ebooks open, it's after example 1, and in section 5.1. So I just got to find it here. Just got to find it. Okay. Okay. All right, so let me bring up the ebook here. Okay, there it is. And if we double click on the screen, it'll make it a little bigger. So, all right, how can we go from a linear combination of a cosine and a sine function to get this form here, form 6 that you see in front of you here? So what they do is they have a rectangle here in figure 5.1.3 where the x coordinate is C2 and the y coordinate C1, and the amplitude is I'm sorry, they have a triangle, right, let me repeat that. They have a right triangle here in figure 5.1.3 where they've labeled the sides as you see them, and the phase shift is the phase shift is phi, and then your amplitude is square root of C1 squared plus C2 squared. Okay, so what they do is they of course the sine, if we call that amplitude A, then based on the picture here, the sine of phi is C1 over A, and the cosine of phi is C2 over A. All right, and so they get this. So they get this right here then. And so the tangent of phi is going to be C1 over C2. But okay, so what they do is they expand equation 6. So equation 6, well, all right, so I want to say this the right way. Eventually, we want to show that equation 6 equals equations. We want to show equation 6 equals this equation 3. If we can do that, then you can see that equation 3 would equal equation 6. That has the phase shift in it. Okay, so you go down here. All right, and the sign, they start here, right, with equation 6, and let me know, okay. And remember, you have an addition formula for the sine function if you have the sine of alpha plus beta. How many remember from trigonometry or maybe pre-calculus addition formulas for sines of sums of angles and cosines of sums of angles? How many remember seeing that in maybe their trig or pre-calculus class? Should be something you've seen. I taught pre-calculus, and I know it's taught in there, but okay, Andrea remembers it. Thank you, Andrea. Well, all right, so if we, thank you, Thomas. So if we have the sine of omega t plus phi in equation 6 here, that can be expressed as as using the addition formula for the sine of the sum of two angles, that can be expressed as what you see in equation 8. Okay, and what they do is they factor out a times the sine of phi and a times the cosine of phi in the terms. And so, but remember, the sine of phi is equal to C1 times A, and the cosine of phi is equal to C2 times A by the way they created the triangle. Well, that means that A times sine of phi is C1, and A times cosine of phi is C2. Okay, and so we can put it back in the formula, and we end up with the position function that you're used to seeing. Antonio, does that help you feel a little more comfortable with the process, why it's true?
Yeah, that makes sense.
Okay, good. And you know, I mean, you know, here using trigonometry, they have an alternative form for this position function that allows you to answer important questions. So it's really beautiful to see how all math comes together. It truly is. Let me point something else out here in the book. So the book has a lot of good examples, and I recommend that you look at them. They will be, I mean, we've covered some good examples to be helpful with homework, but the book examples are good too. I want to just look at example 6 here from the book real quick. So let me find example 6 here. Let me see. Can I maybe just okay? So finding example 6. Yeah. So here, an example. Let me get this a little higher. In example 6, they want you to interpret and solve this initial value problem. So this is like a problem you would see in section 4.4, right? But here in section 5.1, you can interpret that second order differential equation. So in the solution, it says you can interpret the problem as a vibrational system, okay, mass spring system consisting of a mass which is 1/5 slug or kilogram attached to a spring where K equals 2 pounds per feet or newtons per meters. And then the mass is initially released from rest 1/2 unit below the equilibrium position because x of 0 equals 1/2. All right, and x prime of 0 equals 0. Okay. Now, you know, sometimes in problems you'll have examples where, like if the mass is released with a downward velocity of 2 feet per second, okay, well, the downward velocity would mean then that x prime of 0 equals 2. You know, if it's downward 2 feet per second velocity, x prime of 0 equals 2. So you have to be careful with your initial conditions to get them right because, you know, you need them for the problem. The motion's damped and is being driven by an external force beginning at t equals 0. Okay, so how would you solve this differential equation here? Well, all right, you've seen that in section 4.4. The solution for the equation of motion is going to involve a complementary function, and it's going to involve a particular solution, and you add them together. The complementary function or complementary solution comes from the auxiliary equation corresponding to the homogeneous differential equation where the right-hand side equals 0. And the particular function is going to be an educated guess based on 5 times the cosine of 4t. Okay, and you've seen this kind of situation before. All right, and so they work through the problem that they multiply the equation through by 5, okay, to get it in a nice form there. Now, let me just see here one thing on this. One thing. One of their comments here. Yeah, so they say here that intuitively we would expect that even with damping, the system will remain in motion until such time as the forcing function was turned off. Okay, they make that that comment there. Okay, so this function, this forcing function, is like on all the time in the differential equation, the 5 times the cosine of 4t. It's not like those problems where you have on the right side a piecewise function, where the function is on and then it maybe equals 0. You remember the like piecewise function on the right side. It's not like one of those. This external driving force, 5 cosine of 4t, is on all the time. So it's going to be part of the part of the problem. They're going to always be part of the motion. So okay, well let's just go and look at kind of the details of what they do here. So you get a by solving the auxiliary equation, you get a complementary function. And then, based on the fact that the driving force on the right is 5 times the cosine of 4t, your particular solution will be a linear combination of cosine and sine of 4t functions. There's no repeats, notice. There's no repeats. The complementary function has cosine of t's in it, and the particular solution has cosine of 4t. So you don't have to worry about inserting a t or anything like that. But you always have to be on the lookout for that, right, when you do the problems. And so you're going to differentiate your particular solution twice, and then substitute it in the differential equation. And then you're going to solve for your coefficients A and B. Okay, and of course, for taking the derivatives, you can always justify your derivatives using MATLAB to help you. And you'll get a resulting system of equations, and you'll solve for A and B, and it turns out that that then this is the general solution, and then now you want to solve for C1 and C2. So you apply your initial conditions, and then solve for your C1 and C2. Okay, so I know these problems take time, and you'll notice that, like when I, I'll make the assignments visible in a moment. But when you, like section 5.1, I broke that section up into 3 separate pieces. One that was due today, and then one due Sunday, and one due Tuesday, because I know these problems take time to do. And all right, so what's going to happen to this position function? Well, no, wait, hold. Let me go down here. Hold on, let me go down.
Professor, I have a question.
What? Yeah, what happens? Okay, yes, Antonio, yes.
So since you were saying these questions take a lot longer, does that mean there's going to be less like overall questions on the next exam?
Well, of course, the next exam I have to, I have to consider how long questions take. It seemed that, just looking at the times people use to take the exam, anywhere between 2 and 3 hours, so I'm glad I gave 3 hours. So of course, Antonio, I'll be considerate of the time it takes. Of course, I'll be considerate. and you know, I'll just have to I'll figure that out, but I'll be considerate. Let's put it that way.
Sounds good.
I'll keep in mind that it takes time to do these. Okay, sound? All right, all right. So let me ask you here, this equation of motion in this example 6, what's going to happen to, what's the mass going to do as time gets large? What's the mass going to do? Is it going to die down to equilibrium, or is it going to do something else based on that equation of motion? Are there any transient terms in this
Yeah,
this
the first
equation of motion?
term multiplied by e to the negative 3t is transient.
That's right, Michael. So the e to the negative 3t goes to 0. Excellent. Goes to 0 as time gets large. So the first term is going to be transient. Okay, and then you're going to reach then over time steady state. And the steady state portion of the solution is going to be the negative 2500 over 102 cosine of 4t plus 50 over 51 sine of 4t. That's going to be the steady state solution. So you have a transient solution that goes to 0, and you have a steady state solution. Okay, and actually on the next page they have a nice picture. Well, are there any questions on that? Let's make sure people are comfortable with that, because it's of interest to be able to determine what the mass is going to do eventually over time. So this is not an underdamped system. Okay, I mean the first component of the equation of motion in this example 6 is like underdamped, but because of that driving force on the right hand side that's always there, the 5 times the cosine of 4t, as t goes to infinity, x of t approaches the function negative 25 over 102 cosine of 4t plus 50 over 51 sine of 4t. Yes, question? All right, all right. Let me just see here. Going down here. Well, actually, they mention it right here. They mention it right here. The particular solution is a transient term. And the particular solution, yeah, that's a good way. Yeah, the complementary. Let me see here. Yeah, I mean, they're saying what I'm saying. Okay, and they have a figure here, a graph. Let me show you the graph. See here. Okay, of the steady state and transient solution. And of course, the solution that, like the actual solution, which is the sum of the transient and steady state solution, is right there in figure 5.1.14b. So you see in the beginning, why does the graph in this figure start at 1, at x equals 1? by the way? Why does it start at x equals 1?
Is that where it's released from?
That's right. Very good. Very good. In the problem, well, I want to be a little careful. I'm sorry. It's a half, not 1. Looking at that figure, the 1 in B there, and at time equals 0, it's a half, and that's because at the beginning the mass is released. Sorry, the mass is released a half. I've got to be careful here now on my units. Well, it could be either, but let's say it's released a half foot below equilibrium. Okay, and so I've got to be a little bit careful here. Yeah, that's right. That's right. So yeah, I love seeing the pictures too. Are there any questions in general? All right, let me put a stop on the recording.